No, like everything from. Yeah, but we
All right, ladies and gentlemen. So what we have here is we have some data sets here for 3 separate people. All right, and we're going to be able to compare the different data sets, answering those questions down below, which is what we're going to do on the next page. Okay, for the mean and the median, we talked about yesterday, how to get those done on the calculator. If you're just asked mean and median, I don't know if it's worth typing it into that list to be able to get those. Okay, if you're asked more than that, it might be worthwhile, but it's kind of up to you. All right, the dot plot here. This is just another name for kind of a frequency chart here. All right, so what we have here for A is we have data points between what, 1 and 9? All right, and for this dot plot, all we're doing is we're just going to show how many of each one there were. So for example, there was 1 1. There are 2 2s. There are 4 3s. There's 1 4. There's a 7. And there's a 9. What's that? Yes, this is for Terry. All right, so there's your first one. Okay, now if you look at that, okay, what we can say is our data points are kind of skewed to the left. There's more on the left side than there is on the right side, right? We can kind of see that just by looking at it. Okay, so that'll be something that we'll talk about in a little bit. But this would be skewed to the left. All right, and sometimes in the homework, we kind of pay attention to that. That'll go along with what we talk about in the next lesson too. All right, for the next one, for Davis, it's kind of the same concept there. All right, this one, he only had, what, between 1 and 4? I mean, technically you could do 1 through 9 here, but I don't think there's any point to it. You could just put down the data that is available for him. So we've got 2 1s, we've got a 2, and then we've got 5 3s, and we've got 2 4s here. All right, would this be skewed one way or the other? Are there more on one half than the other half? Well, there's more on the right side than there is the left side, right? So this, we could say, is skewed to the right. Okay, it's not as obvious as this top one was, all right, because technically we still have most of our data points kind of in the middle, but you could make the case that this is skewed to the right. And then for our last one, for Maris, we have data points here, let's see, 2 through 8. All right, so we have 1 2, 2 3s, 3 4s. We have 3 6s. And we have an 8. All right, this one's a little bit more interesting. Is this one skewed one way or the other? Maybe a tiny little bit left. I mean, technically, if this would be the halfway mark, yes, there are 2 more on the left side than the right side, but this would be pretty close to symmetrical. All right, so if you had to pick either skewed left or skewed right, okay, we would say that it's skewed to the left. Or for this one, we could say it's pretty symmetrical too. Okay, so this one, you could say either one of them and you would not be wrong with this one. Okay, now that would be for part A. For part A, it just said make a dot plot and then compare the shapes. So how we compare the shapes is we can say these parts about the skewed part. Okay, for part B, you guys know how to find the mean. You would just add up all the points and divide by how many we have. All right, so go ahead and do that for me really quick, please. That means calculator, let's go.
Right?
3.7 for Terry. Okay, I would agree with that. What else do we have? What's that? 2.7 for Davis. Yep, I'd agree. What do we have for Maris's average? What is it? 4.6. That's what I got also. Okay, so you just add those numbers together, divide by however many we have there. All right, 4 to find the median for each one of them. That's letter C. To find the median, what do we have to do? We have to find which number's in the middle, right? Okay, now technically you could go off of our dot plot here, couldn't you? We have 10 data points, so we are looking for data point 5 and data point 6, right? So 1, 2, 3, 4, 5, 6. For Terry, our 2 in the middle would both be 3s. So our median for Terry would be a 3. Okay, so there's 10 data points here, right? So the 2 middle numbers would be number 5 and number 6. That'd be your middle. So 1, 2, 3, 4, 5, 6. It'd be those 2. All right. 4, is there 10 for all of these? Yeah, there's 10 for all of them. All right, so we're looking for data point 5 and 6 for each one of these. So 1, 2, 3, 4, 5, 6. It'd be a 3 for Davis also. For Maris, 1, 2, 3, 4, 5, 6. Looks like it'd be a 4 for Maris. Yeah. All right. Any questions on how to find those off of the data or off of the dot plots there? We just kind of count them up. All right. What you guys used to do way back when you started doing this the first time, you crossed these off as you went and then found the middle two. That's fine. You can still do that. All right. Just make it nice and light since it's actually part of one of your other answers, but you could definitely do that. All right. So that's letter C. For letter D here, I don't remember what it asks. Describe any pattern you notice between the shape and the measures of the center. Now, the measure of the center are both your mean and your median. All right. So for Terry, we said the mean was 3.7 and the median was 3. All right. What do you notice? I mean, if both of those are basically right in here, what do you notice about the shape of the graph compared to both the median and the mean? It seems accurate, like the middle seems accurate. Okay, the only problem with this one is that it really tails off here to get these last 2 in. Okay, so the only thing that I would say about the shape is that for Terry's, the mean is affected more because of these two numbers out here at the end. And those would kind of be our outliers. Remember, we have an equation to find the outliers. Okay, so that's why they're not exact, or I mean, they're still fairly close to the same with our 3 and our 3.7, but there's a little bit of a difference there. All right, if you look at Davis's, if we look at this, our mean is 2.7, our median is 3. They're almost right on top of each other. And if we look at that graph, well, that's where most of our data points are, aren't they? Okay, so because of that, Davis's is pretty symmetrical around the mean and the median. And then we've got one more left to go here. We've got Maris's. We know that Maris's median is a 4, and the mean is 4.6. So these are a little bit further away. So I would guess, based on our mean being a little bit higher than the median, there's probably a data point that kind of affects our average more. And if we look at that, that's kind of what this 8 is, isn't it? Okay, it's kind of off by itself here. So I don't know if it's an outlier. We'd have to run it through that equation we talked about before. But the mean definitely is affected by that 8. All right, now with those outliers, if you looked at both our top graph here and our bottom graph, if we were just able to take out this 7 and this 9, these would all be pretty symmetrical. It'd still lean a little bit one way, okay? But it wouldn't lean very much. If we came down here and took out just the 8 here, those are all kind of in the same spot. All right, so it'd be very, very symmetrical. Okay, what you are looking for to be able to tell with how you construct these is if your mean and your median are very close to the same, kind of like it was for the second one, then it's going to be very, very symmetrical. Okay, if there's a big gap between them, and that's kind of what we were starting to get between our 3.7 here and our 3. If there's starting to be a bigger gap there, that means you've got some data points that really played into it quite a bit. Okay, now, even saying that though, you have to be careful with that, because if we have the 7 and our 9 in here, and say we had a data point way over here, this data point could equal out with that 9, couldn't it? And say if I had another one over here, this data point could equal out with this 7. So then that would make our mean and our median very, very close to each other. So you wouldn't necessarily be able to see that, yeah, we could still have outliers. You wouldn't be able to see that based on your mean and your median could be exactly the same there. Right, so you're going to have to look at your actual data points. You're going to have to look at the actual graph sometimes to be able to see if there are outliers with that drastically affect your mean. All right, as we talked about the other day, sometimes the median is a better way to see what the middle of all your data points looks like, because the outliers won't have a huge effect on it. Okay, So any questions with how to do this stuff? I mean, I think overall it's pretty straightforward. Okay, and it's just answering different questions that's going to be asked of you. All right, any questions there at all? All right, that is not you guys. We'll go here. All right, that was it for 2.6. Good solid 2 or 3 slides. 2.7, this one's a little bit longer. There's more in this one. All right, 2.7, we are talking about standard deviation and what it actually means. So I know in your past classes, we did find standard deviation. Now, unfortunately for this, there are 2 separate equations for standard deviation now. The one that we did is going to be one of them, but the other one is adjusted just a tiny little bit. All right, so standard deviation, really all it measures is how far the data points are from the mean. All right, there are a couple rules to it. First of all, your standard deviation will always be positive. It is possible for it to be 0. If it were to be 0, that would mean all of the data points are exactly on the average, on your mean. All right, as it says down below, if the standard deviation is very small, that does mean that all of your data points are really, really close to the mean. If it is large, the data points could be more spread out from the mean. Or a better example would be, say that I gave you guys a test and the average was a 63%. And there's 22 of you in here and 20 of you got a 60%. And the other 2 ended up getting in the 90s. All right, so your standard deviation could get much bigger because of those 2 data points being a long ways away from the average. So that's why I said it could be more spread out. All right. Traditionally, what we do see is the bigger the standard deviation is, though, the more spread out all of the data points are. All right. And we're going to talk about that. Even though they're more spread out, there is still a certain percentage of data points that should be fairly close to the mean. All right, now, as I said, there are 2 formulas for standard deviation. The one that you guys did in the past was the population standard deviation, okay? And what that was we took each number minus our mean and then squared it, and then we added that to the next number minus the mean and squared it, and we keep going until we get all of the numbers in there. Okay, then after we do that, we divide by how many numbers we have, and we take the square root. All right, that's the equation that you guys have done before. And that is for the general population. So if you're talking a huge population of numbers here, that would be the example for it. Okay, if you are only doing a sample of it, the equation changes just a tiny little bit. In fact, the top is exactly the same. It's still going to be x minus the mean. So each number minus the mean squared. And then you add them all together. And that's going to go on until you get all the data points in there. And then we're going to divide by a different number. Okay, that number is simply how many points are in your sample minus 1. And then you still take the square root. All right, so population is just the regular n. The sample is n minus 1. Okay, now, for those of you with graphing calculators, I'm going to show you that it's not that big of a deal. We're going to be able to solve that in just a second. Okay, but the question would be what should your question be between these two equations? Why is this an n minus 1, right? Okay, that's a great question, Eli. Okay, why do we divide by n minus 1 instead of an n? Okay, remember it's just for the sample, and the sample is an estimate of the entire population. Okay, and because it's just a sample, when we divide by n minus 1, it's going to give us a better estimate of the entire population's standard deviation. So that's why we do it. At least that's how I understood it out of the book. All right. So we're going to come back here to do this. Yep. Mm-hmm. Yeah. All right. So for this, we've got a whole bunch of data points there. And as you guys know, with graphing calculators, you're able to do this entire problem with the calculator. Okay. Now, for those of you who have one, if you want one, just talk to me, we'll figure it out. Okay. I'm going to do this. Okay. You could spend all of the time typing in every single one of those data points, but you don't have to on the calculator. The calculator is smart enough that if you put it in the way that I'm going to show you here, that it can do all that stuff for you. Okay? So the different data points that we have are 9, 9.5, 10, 10.5, 11, and 11.5. Okay? So what we're going to do is we still need to go put it into our list that we had in the calculator before. So we're going to go to Stat. We're going to go to Edit. There's our list. I'm going to get rid of these numbers here. Okay, now, where you put these is very important here. In L1, we want to put our actual numbers there. But notice I am not going to put in both of the 9.5s or all of the 10s. I'm just going to put down the different numbers here. All right, so those are our different numbers there. From there, what we want to do, is in the L2 column, we want to say how many of each one we have. And if we do that, then it's going to take care of all of those. Okay, so like Morgan, for your calculator, I don't know if you can do this or not. Yeah, can you? You have 2 lists there? Yeah. Okay, so yours might take a little bit longer to get it figured out, but should be the same concept, hopefully. All right, so for the 9, we only have 1 of them. So we put 1 in there. 9.5, we've got 2 of them. And 4 of them. 10.5, we have 4 of them. 11, 6. And 11.5, we have 3 of them. Okay, so if everything goes according to plan, I didn't have a calculator at home, so I didn't test this out this morning, but hopefully this all works good. Okay, what this is showing is L1 is the actual data points, L2 is how many of each one we have. Okay, so then we want the calculator to go work for us. Okay, so go back to Stats. We want it to calculate. We only have 1 variable, so we're going to put that there as L1. Hold on just a second. That's what I thought. If we go here to the 1 variable statistic, the frequency list. Okay. That's how many of each one that we have. So I put it into my L2 column. So I need to actually type in that L2 button. Okay? The L2 is right above the 2. So you have to hit the blue button.
Oh, okay.
All right, and then let's see. All right. And then how I knew right away the first time I put that in that it was wrong was that I looked at this n value here. Remember, n stands for how many numbers we have there. Okay, right away it said 6. That's how I knew that I didn't do it right. Okay, there I believe are 20 data points up there. So that would back that up for us. Okay, yes, dude. The second one in, so that you are probably gonna have to skip that. Okay, so at least you have a way to get there. Okay. Okay. We might be able to look at that and see if we can fix that somewhere. Okay. All right. Now for this. Okay. Even the differences between those standard deviation equations, this will, our calculator will help us out with it. We just got to know what it's talking about. Okay. First one, it says find the mean. Okay, our mean is x bar, so that's the 10.525. All right, you add all those together, divide by 20, you should get that also. Okay, or our sample standard deviation. Now that's the n-1 thing, right? Okay, and I know the calc kids asked me last year, what does that S mean and what does that O mean? Okay, and I couldn't tell you because I couldn't remember. Now I know what it means, right? The S stands for your sample standard deviation, okay? So you don't have to manually figure that out. The calculator is going to do it for us. The sample standard deviation would be this point, 716. All right? Okay? If you were asked if that was the entire population of all fifth graders, and they asked us to find the actual standard deviation, that would be the one down below. So the 0.69. All right? So there's the difference between the two. S stands for sample standard deviation. The omega stands for the population standard deviation. Okay? So we're going to use those to find our last two properties. All right, any questions on how to find that with the calculator? Morgan, did you get it figured out? Very good. Okay. All right, so standard deviations, how we use that is we're going to be asked sometimes to find, all right, what is the value 2 standard deviations below the mean? Well, we know that our mean is 10.525. We know that our sample standard deviation is, what did I say, 0.716. 716. And we want to take 2 of them below the mean. So this would end up being our equation. We would take 2 times our 0.716 and subtract that from 10.525. And what do we get for an answer there? What's that? Because that's what this question was asking. It was asking for the sample standard deviation right there. Oh, well, in the problem itself, it says that this is just a sample of all fifth graders, okay? They would have to tell you whether it's a sample or the entire population. All right, what do we get for an answer, people? Say that again. 9.093. That makes sense to me. I think that's right. Deidre agrees. Okay, perfect. Do we have any other questions? Okay, so think about this next one then. Values of 1.5 standard deviations from the mean. Okay, so when it says from, it's not saying above or below, it's saying from. So we're going to have two answers here. We're going to have 1.5 below and then 1.5 above. So what's the equation to find the one for below? What do you think? Okay, what are we subtracting? 1.5 times our 0.716. And then for the one above, it's going to be plus 1.5 times 0.716. And what do we get for those answers? Say that again, Eli. 451. Okay. 5, 9, 9. All right, perfect. Okay. Okay. So any questions on those? All right. So we went over this page. All right. This one. Yeah. Finding the standard deviation from the following frequency charts. Okay, so the nice thing is we can use the calculator to be able to do this, just like we did on the last page. But what's different with this frequency chart? Right, we've got these ranges again. So what are we going to plug in there? We're going to plug in the middle of it, right? So in that L1 column, we're not going to put 0 through 2. We're going to put a what? A 1. For 3 through 5, we're putting a 4. 6 through 8, we're putting a 7, and so on, right? We're just putting the middle value in there. And then we're going to plug in the frequency into that L2. All right, so go ahead and do that. See what you get for an answer here. I don't remember if I figured this out. What's that? Oh, good question. All right, does this say it whether it's a sample or a population? Whenever it doesn't say, I believe we are trying to find the population. No, we're doing the population. What'd you get, Max? That is correct. Okay. Got it figured out back here? That would make it a touch easier. Like, good luck doing this without, huh? Yes, ma'am. Try it. Yes, $10. Okay. All right. What? Did you not get the right answer? You didn't do an answer. Yes, you probably did something wrong. Well, you see how this bottom one doesn't have a thing at the top? Or you just have that there. All right, now it's over. Oh. All right, TI Inspire people, do we get it figured out? For the rest of you, Morgan, you're good on your little tiny calculator? Huh? 7 pages. Last one's a homework assignment. Huh? 4. We're almost done. And Autumn, after we're done, I'll take a look at your calculator, see if we can get it figured out. Okay? You do? For sure? All right, while you guys are waiting, you guys can copy this down. Yeah, because you didn't learn it last year. I taught it. There you go. Pretty well. Well, Abigail, when you did this in school, we were actually in the building. So Sarah was not in the building.
You're not reading.
Yeah, I'm reading this, which is our stats book. All right, so next thing we got to talk about is what's called a z-score. The z-score is simply the number of standard deviations above or below the mean, okay? And a z-score is a nice way to be able to figure out when you have 2 different sets of data like we have down below, which one is better, okay? And so we're going to be able to figure that out with like down below this line is all an example here, okay? I don't even want to know what school this is where you can get a GPA of 77, but that was the example that I was given. So I'm like, we'll run with it. Huh?
It's like some schools do it by your grade. It's like in my cousin's school, they have like 99 as their GPA versus 4.0.
Oh, okay. I didn't even know that was a thing.
My mom graduated with a 97 GPA, which means like a 4.0.
So she's smarter than you. If you get a 97, it's more than a 4. Come on.
Well, it's based on the type.
I mean, any football player can tell you that 97 is more than 4. Eli, would you agree with that? Yeah, would you agree with that? Just a 4. So, the traditional football player, Caitlin, can tell you.
Difference between, there's like interval and like,
Yeah.
I don't know what the other one is.
Yeah, I don't know. I had never heard of it before I read this, but I knew there was extra stuff out there. Just how they figure it out
Yeah,
is
my
different.
cousin's school's like Lakota.
Okay.
Because they always say like, oh, I have a 90 GPA. I'm like, I was like, I got not that. I got
Yes.
a 4.4.
All right, so take a look there. Okay, gentlemen. All right, so we've got 2 different students from very different high schools wanted to figure out who had the highest GPA when compared to their school. Which student had the highest GPA? I don't know why I wrote that again. Sorry about that. I could have just put a question mark right here at the end, but oh well. Okay, so our goal here is compared to the school averages. Who has, compared to the school, which student is smarter? Okay. Now, does that necessarily mean that this person is definitely going to be smarter? Not necessarily.
Oh, the other person knows probably too.
It could be. We're going to figure that out. Okay. The one thing that we know for sure is both John and Allie, their GPAs are below the school's average GPA. All right. So if one is above and one is below, then it'd be pretty easy to tell. Well, the one above is above the mean is going to be the better compared to the other one. Okay. But for this one, we're going to have to figure it out using both the standard deviation and the school average along with their actual GPA. So all we do is we're going to find each one of their z-scores. So John's is going to be 2.85 minus the school average, which is a 3, and then we divide it by the standard deviation. And that would get us approximately a negative 0.21. Okay, so yes, ma'am. You can have a negative z-score. A negative, what does a negative z-score mean? What do you think? It just means it's below the average. That's all it means, okay? If it's between 0 and 1, that means it's not quite one standard deviation, okay? So it's just a little bit below the average, okay? For Allie's then, we're gonna do the same thing. We're gonna take her value minus the mean and divide by standard deviation. So this would be a negative 0.3. So which student had the highest GPA when compared to their school? It was John's. Okay.
The higher the better.
The higher the better. Yep. Okay. All right. Any questions there? Standard or z-scores, as long as you have the equation, the concept is pretty straightforward. All right. Now, this one, okay, just take a look at this. Okay, hopefully some of these numbers are familiar. All right, if the distribution is normal and is a bell curve, all right, so it looks more like this. Okay, these three numbers are very, very important. Okay, one standard deviation from the mean is 68%. 2 standard deviations is 95. And 3 is 99.7. Okay, so those 3 you absolutely have to know. All right, as we go for forward stats wise. Okay, these 3, I'm going to be honest with you, I've never heard of these 3 before. So I don't know how important they are. Okay, but what it does say is these 3 up above are if it's a perfect bell curve. You know, on the first one, we kind of had a shape like this. Okay, that's not really a bell, is it? Okay, it's skewed to the left. Okay, if it's skewed to the left or skewed to the right, okay, this is not going to work. But if it's a bell, kind of like what we have here, then these 3 would work. But no matter the shape, 75% of the data points will fall within 2 standard deviations of the mean. 89% will fall within 3 standard deviations of the mean. And 95 will have, or 95% is within 4.5 standard deviations from the mean. Okay. Like I said before, I don't know how important these 3 numbers are, okay, because I had never heard of them before. All right. Okay. Yeah. Well, you can if you need to. It should be a shape that you recognize. Yeah. No. All right. Any questions here? All right. You have 2 separate homework assignments then. Okay. First of all, out of the book. I know that this is really big, but listen really carefully here. Okay. Like they have them broken up as like, say lesson 50 or number 55 is to do a box plot like we did right away today. Number 56 is find the mean. 57 is find the median. 58 is find the mode, and so on. Okay, so while this looks much bigger, it might actually be it might take you just as long as some of the rest of them to do. Okay, the other thing that I need you to do, this is important for Friday. First of all, you need to count the number of shoes that you own. All right, some of you might be able to do it while you're sitting here. Others of you might have to go home and take an inventory. All right,
Oh, it's like pairs? Or like-
pairs. Yeah, pairs of shoes. Okay. Yes. Okay. So, for example, I have 2 pairs of tennis shoes, 1 pair of dress shoes, and 2 pairs of sandals. So I would have 5 pairs. Okay. You guys figure out how many you need. We need that for what you're going to do in class on Friday.
What if I share shoes? Are they mine?
We're going to assume that you own them. You share them with your sister?
And I'm all- we're all
Oh.
the same.
Oh, okay.
Maybe
Sure.
a stat